What is up, guys? This is Weasel for PokerWeasel.com. Welcome to part 6 of the Core Maths series. In this video we're going to be talking about EV calculations. We're going to see plenty of examples of calculating expectation using the EV formula. Let's get right into it by having a look at the formula used for calculating expectation, or EV. Just so we're completely clear, EV stands for expected value. It essentially tells us how much we make or lose on average in a given poker situation. Here's the formula for calculating EV. There are 4 terms in this formula. The first is P winning. Now that means probability of winning. That's going to be expressed as a decimal, as we learned in the previous part of this series. Probability of winning multiplied by the amount we win. Subtract from this, i.e. minus the probability of losing multiplied by the amount we lose. This is a very simple formula, and I recommend at this stage that you just memorize it. It can't take you more than a few minutes to memorize this formula, and the applications of this formula are very broad. It's going to help you in a wide variety of poker situations that involve maths. So it can't hurt you right now just to memorize this formula. It's going to come up again and again throughout your poker career. Perhaps one thing that might help us to memorize it is to give it some context by having a look at an example. We open raise the button to 3 big blinds. The small blind and the big blind either 3-bet or fold. They don't cold call. Cumulatively, both blinds fold 70% of the time. If we are 3-bet, we fold. In other words, either we pick up the pot here because both blinds fold, or one of them 3-bets, that's going to happen about 30% of the time, we fold and we lose the hand. What is our expectation? We can use a formula to calculate this. Step number 1, if you're not used to using formulas and this is a bit daunting for you, the first step is simply to list our 4 terms. There are 4 terms in this formula. Let's list them. Term number 1, the probability of winning. How likely is it that we will win here? Well, both blinds fold 70% of the time. Our probability of winning is 70%, but of course we have to express that as a decimal, 0.7. What is the probability of losing? Because nowhere in this question does it actually tell us directly what the probability of losing is. However, we can figure that out using a simple process of deduction, because there are only 2 outcomes here. Either we win or we lose. So if our probability of winning is 70%, our probability of losing has to be 30%. So that 0.3 wasn't mentioned in the question anywhere. We've just used a simple process of deduction to figure out that if the blinds fold 70% of the time, then 30% of the time one of the 2 players is going to 3-bet and we're going to lose the pot according to the question. What about amount 1? So the amount we stand to win if we end up winning. Well, if we steal the blinds, we essentially win anything that's in the blind. So that's 1 big blind from the big blind, 0.5 from the small blind. Amount 1 is 1.5 BB. Amount lost, we're investing 3 big blinds on our steal. So if we have to fold that in the face of 3-bet, then we're down 3 big blinds. So amount 1, 1.5. Amount lost, 3 big blinds. Okay, that's the first step out of the way. The second step is to take our 4 terms and input them into the formula in their respective positions. So that's what we've done here. 0.7 times 1.5 minus 0.3 times 3 equals our expectation. Now just a word on maths. We did say we're not going to skip over anything. We're going to pretend you don't know anything about maths. When you have brackets like this in a mathematical equation, the rule is simple. You have to do the calculation that's in the brackets first before you can proceed with the rest of the calculation. So we have to multiply 0.7 by 1.5, and we also have to multiply 0.3 times 3. We're not even going to deal with that minus sign in the middle of the formula until we've solved the sum in the brackets. Think of it as a sum within a bigger equation. So if we do that, we get these values. The first bracket, 0.7 times 1.5, that translates to 1.05 when you multiply those 2 numbers together. 0.3 times by 3 is 0.9. So now we've got rid of the brackets, because once we've solved the sum in the brackets, we can remove those brackets, like we've done with the 0.9, although we haven't done it with the 1.05. But you can remove all of those brackets. We're left with 1.05 minus 0.9. So if we do that on the calculator, we get 0.15 BB. By the way, if we wanted to be technically correct here, when we input the values into the formula, where we've got 1.5 and 3, we should also put BB in the formula, just so we know that we're talking about BB and not just numbers. So that's how we should do it if we want to be technically correct. But we just know we're talking about big blinds anyway, and the result is 0.15 big blinds. So this here illustrates the concept of automatic profit, something we've discussed earlier in the series. This is a situation where we're not taking into account any post-flop expectation, but purely based on our pre-flop expectation, we generate 0.15 big blinds every time we do this. In fact, we can even test our answer and see if it's reasonable by checking to see whether this scenario should generate automatic profit. So hopefully remember that the break-even point on a bluff is the same as the amount of the pot we invest in terms of percentage. So here we're investing 3 big blinds with our button open into a total pot of 4.5 when you add everything together, including the big blinds 1 big blind and the small blind 0.5. So if we do 3 divided by 4.5, we will get the break-even point on our bluff here. 0.66. So what does that mean when translated? It means that if our steal attempt works more than 66.66% of the time, we generate automatic profit. Well, what did our questioner say? It said that both blinds fold cumulatively 70% of the time, which is above this automatic profit threshold, but only by a few percent. So what can we deduce from this? That our expectation should be positive because we are above the automatic profit threshold, but it's probably going to be on the low side. When we see our result of 0.15 big blinds, we verified that it seems to be within about the right region of results we'd expect. It's plus EV, but only slightly plus EV, 0.15 BB. Of course, in the context of an actual poker game, 0.15 BB profit every single time it's folded round to us on the button is huge. Remember, win rates are not very big in poker. We might expect a good player to maybe have 6 or 7 big blinds per 100 hands, whereas here, when we open the button, when we generate 0.15 BB per hand, we're actually generating 15 BB per 100 hands. So very, very significant and profitable for us. And that's assuming that we always fold against 3-bets and our opponents never cold call. When we start defending against some 3-bets, when our opponents start cold calling and we have some post-flop expectation, we're going to be making more than 15 BB per 100 hands in this scenario. It's going to be very profitable for us, in fact. We can actually use the EV formula in a reverse way to calculate break-even points. I'm going to jump into something that's slightly more complex at the beginning of the video, then we're going to proceed with some simpler stuff. We're going to be having a look at a branch of mathematics known as algebra. The idea behind algebra is essentially substituting letters in the place of certain values to help us calculate what those values should be. Don't worry if it sounds abstract at this stage, we can have a look at an example, but you may need to concentrate if you have not been exposed to algebra in the past. You could find this slightly complex, but it's an important discipline for poker players to have, so definitely pay attention. We open raise the button to 3 big blinds, blinds either 3-bet or fold. Okay, everything's the same so far. Use the EV formula to demonstrate the break-even point of the bluff. Now we're deliberately doing it this way. We already know what the break-even point of the bluff is. We've just calculated it on the calculator at 66.66. So the idea here is we're going to be able to verify whether we're using the EV formula correctly, because that's the result we should end up with. If we don't end up with that result, then we're not doing this in the correct way. Now we might think, what's the point of this? We can just calculate the break-even point very easily, 3 divided by 4.5. What's the point of doing something complicated with algebra? Well, the idea here is that 3 divided by 4.5 calculation works very well in situations where we're looking at zero equity bluffs, i.e. either our steal attempt works or it doesn't, pot equity doesn't factor into that. But you can't use a simple calculator to figure out situations where we also have pot equity. So our steal attempt works some of the time, but we also have some pot equity if called. In order to calculate the break-even point in these scenarios where we also have pot equity, it's necessary for us to use the EV formula. So although it's not strictly necessary for us to use the EV formula in this instance when we're only dealing with fold equity, we're using it as a simplified example to introduce you to the concept of solving for break-even points using algebra. As we mentioned, the idea behind algebra is substituting letters to represent certain numbers. So this is what we're going to do right off the bat. We're going to say the letter X is going to represent the cumulative amount of folds we get from both blinds. In other words, our success frequency, our fold equity, how much we win the pot. These are all terms that mean the same thing. In the question we just looked at, X would have been 0.7 because we said that both blinds were folding 70% of the time cumulatively. So that's what X represents. We know in this case that X is hopefully going to end up being 0.666, but pretend we don't know that yet. That's what we're trying to figure out. So X, cumulative amount of folds we get from both blinds. Now let's define our terms in exactly the same way, so we can use the same methodology here. What is the probability of winning? It's X. X is an unknown decimal at this stage. So if the probability of winning is X, what's the probability of losing? Well, remember that before we used a process of deduction to figure this out. And we saw that if the probability of winning was 0.7, then the probability of losing had to be 0.3 by a process of deduction. The decimals have to add up to 1 or 100% to make sure that all possible events are covered. So if the probability of winning is X, then the probability of losing is 1 minus X. So in the case of 0.7, the probability of losing was 0.3 because 1 minus 0.7 is 0.3. Okay, so those are our first two terms represented algebraically. We're using the letter X to define this term. What's the amount won? It's the same, okay? We can still win the amount that's in the blinds, 1.5. Amount lost, 3 big blinds. Everything's the same with those last two terms. It's just this X that's appearing in the first two terms here. Now, we know something that we didn't know before. Because you see, in the previous question, we were trying to figure out what the EV was. But this time we already know what the EV is. How do we know that? The idea here is we're trying to demonstrate the break-even point of the bluff. So what is our EV if we are exactly breaking even in a certain point? Hopefully it's pretty straightforward. Our EV is going to be 0. And this is the key to solving this question. You write out the EV formula, then you put equals 0. We already know the expectation, it's 0. What we have to do is find the value of X, which allows this equation to be 0. That's going to be our break-even point. So if you're already familiar with algebra, sorry if this is painstakingly slow, but we want to do this series in a way where even if you have no exposure to the maths of poker, you can still hopefully get to grips with this. So we have to go quite slowly. It is somewhat complex if this is the first time you've ever looked at an algebraic equation. So how do we figure out a value for X? Well, we can use certain tricks. This looks quite daunting at first, but there's certain things we can do to solve a formula, and actually it's not that difficult when you know how to do it. So how do we do it? Well, let's stick to our rule. Step number 1, always to multiply out the brackets. X multiplied by 1.5, 1.5x. 1.5x, we've put those two terms together. That's just the same as saying 1.5 times by x. So 1.5x in BB. Remember we said that technically we're supposed to leave that BB there in the formula. So 1.5x minus, now multiplying out that second bracket is a little bit more complex. When you have a bracket within a bracket like this, and you're multiplying it by another term, you have to multiply every term in that bracket by the other term. In other words, we're going to do 1 times by 3 big blinds, and also minus x times by 3 big blinds. So 1 times by 3 big blinds is going to be 3 big blinds, pretty straightforward. Minus x times by 3 big blinds is going to be minus 3x big blinds. So in that bracket right now we have 3 big blinds minus 3x big blinds. Now one final difficulty here is that because we're in a situation where we have minus, and then inside that second bracket we have minus 3x big blinds. Well, just think about it this way. If I told you to do the sum, what is 2 minus 2? You would tell me it's 0. Very, very easy arithmetic there. But what is 2 minus minus 2? Well, when we start subtracting a negative number, it's the same as adding that number. So you can see that before that second bracket there we have a minus. So when we have something like minus 3x, that becomes plus 3x. Whereas the 3 big blinds, which was positive, That just has a minus in front of it. Has a minus and a plus, I guess you could say, which is essentially a minus overall. So you can see, although the terms within that bracket were originally 3 big blinds and minus 3x, because that bracket is preceded by a minus, those terms have now become minus 3 big blinds plus 3x big blinds. Again, that should ideally have the big blinds in front of it. We just haven't done that. But it should say 3x big blinds. So now we've multiplied out the brackets, so we get this 1.5x big blinds minus 3 big blinds plus 3x big blinds equals 0. So now is where the next algebraic trick comes in. So number 1 is multiplying out the brackets first. Number 2 is rearranging this equation so that we can solve for x. Now the reason why it's called an equation is very specifically because it has an equal sign. If something doesn't have an equal sign, then it's not an equation. But this has an equal sign. And what we can do is we can move terms from one side of the equation to the other side. And by the other side of the equation, we mean the other side of the equal sign. The only rule is when we move something from one side of the equation to the other side, it becomes inverted. It's like there are two different parallel universes either side of the equal sign. On the left-hand side, if something's positive, it becomes negative when you move it over to the right-hand side. If it's multiplied by a certain term on the left-hand side of the equation, it becomes divided by that term on the right-hand side of the equation. So let's see how that works. Before we do that, however, there's some simplification that we can use here, because we have two terms which are the same. We have 1.5x big blinds and we have 3x big blinds. Because both of these terms are counting things in x big blinds, we can just add or subtract those terms from each other. So we have 1.5x plus 3x. So now we have an equation that says 4.5x minus 3 big blinds equals 0. But we can move that minus 3 big blinds to the other side of the equation, but it becomes a positive version of 3 big blinds. So 4.5x equals 3 big blinds, or plus 3 big blinds, but when something's positive, we don't need to put the plus, we just assume it's positive. It's only when things are negative that we need to specify. So we have 4.5x equals 3 big blinds, and we know that 4.5x, that's the same as saying 4.5 multiplied by x equals 3 big blinds. So if on the left-hand side of the equation we have multiplied by x, then if we were to move it over to the right-hand side, it would become divide by x. And we can't really divide by x, it's not possible, but obviously 4.5 times x, that's the same as saying x times by 4.5 as well. Those two terms are interchangeable. So what we can do is we can take that 4.5, move it over to the right-hand side of the equation. Instead of being times 4.5 on the left, or multiplied by 4.5 on the left, it becomes divided by 4.5 on the right-hand side. So now we have an equation which reads x equals 3 divided by 4.5. Well, great, that's something we can solve. In fact, that 3 divided by 4.5 is the same calculation we ran in the previous slide, because we're risking 3 big blinds into a total pot of 4.5 big blinds. So what do we get when we divide 3 by 4.5? We get 0.66667. That's the decimal representation of how often we need our bluff to succeed in order to break even. We knew it was going to be that. The fact that we've come out with this answer, 66.667%, as the break-even point of the bluff, means that we have used the EV formula successfully to demonstrate the break-even point. Now, in terms of doing EV calculations by hand, it doesn't get a lot more complicated than this. If it gets a lot more complicated than this, we'll generally resort to using software to run EV calculations rather than doing it by hand in this manner. Okay, let's continue with what we'll describe as an equity scenario. This is going to be different from the fold equity scenarios we've looked at. So we've looked at a situation where we're interested in how much fold equity we're generating. Let's look at a situation where our EV is dependent on the amount of pot equity that we have. If you've understood everything so far, this question should be relatively straightforward. So flop scenario, 100 in the middle, we call a $50 all-in when we have 20% pot equity. What is our expectation? Now once again, we can use existing knowledge to make estimates regarding what our expectation might look like in this spot. We can do a simple pot odds calculation. For example, if we call this 50, what percentage of the total pot would we be investing? Well, there's 100 in the middle, there's villain's 50, there's our 50. We'd be investing 50 into a total pot of 200. or otherwise known as 25% of the pot. So we're in a situation where we're investing 25% of the pot, but we only have 20% pot equity. That should tell us straight away that the expectation we're looking for as a result of using our EV formula is going to be negative. We're going to make a loss with this call. How much do we lose on average? That's when we can start plugging our terms into the EV formula. Let's start by defining our terms. Probability of winning, 0.2. We win 20% of the time as a result of our 20% pot equity. Probability of losing, once again using a process of deduction, we can set this at 0.8 or 80%. Amount 1. You have to be a little bit careful here. We know that there is going to be 200 in the middle, but we're not winning 200. We are going to be winning the 100 that's already in the middle and also the $50 that our opponent is betting. So we're actually standing to win $150 if we win at showdown here. Amount lost, that's just the amount we are calling, which is $50 in this case. Okay, we've defined our 4 terms. The next step is simply to input them into the EV formula. So we get 0.2 times by 150 minus 0.8 times by $50 equals our expectation. As usual, let's start by multiplying out the brackets. So 0.2 times by 150 gives us the result $30. 0.8 times by $50 gives us the result $40. $30 minus $40 equals minus $10. So on average, we lose $10 every single time we make this losing call. So if having 20% equity causes us to lose money, we can now proceed onto this question. Same setup. $100 in the middle, we face a $50 bet from our opponent. Calculate the required equity for us to break even. So it's another calculate the break even point question. The difference is now we're not looking at the break even point as a result of how many folds we need. We're looking at the break even point regarding how much pot equity we need. The good news is everything is exactly the same. This is mainly here so you can practice your calculate the break even point skills using the EV formula. So take a moment, pause the video. Remember, start off by defining the terms. When you've done that, input them into the EV formula, multiply out the brackets first, then rearrange the formula after you've set it to equal 0 to find out the value of your variable. So in this case, we're going to refer to the variable x to denote the amount of pot equity we have in the hand. Okay, hopefully you've done that already. Now you can check your answers. So here are our 4 terms. Probability of winning x, probability of losing 1 minus x, amount won 150, amount lost $50. By the way, you probably realize that you can use your knowledge of pot odds to answer this question without needing to find the break-even point. So we really are doing this purely to practice our algebra. In terms of pot odds, we realize that we are investing 25% of the pot, $50 into a total of 200. Therefore, if we have exactly 25% pot equity, it means we're going to break even. So we already know the answer we're looking for. We're just seeing if we can demonstrate that using algebra. We have our terms. Next step is to put the terms into the formula and set the formula to equal 0 because we know that at the break-even point our expectation is going to be 0. Multiply out the terms. We have 150x in the first bracket. The second bracket is going to be 50 and minus 50x. But because the entire bracket is being subtracted, that becomes minus $50 and plus 50x dollars equals 0. So similar to before, we can add the terms 150x and 50x together to get 200x. 200x equals $50. It was minus 50 on the left-hand side of the equation. When we move it over to the right-hand side, the sign is inverted. It becomes positive $50. Next stage is simply to leave x on its own. And that's the general goal when we're moving things from one side of the equation to the other. The goal is to get x on its own on one side with some kind of mathematical function on the other side so we can establish a value for x. So right now we have 200 and x on the same side. We need to move that 200 over to the other side. So on the left hand side it's multiplied by 200. If we move it over to the right hand side, we get x equals 50 divided by 200. Notice once again that this is the same math we just did in terms of figuring out what percentage of the total pot we are investing. So why not just use our knowledge of pot odds? Again, we're learning the algebra using a very simple question so that we can also find the break-even point of more complex questions which involve both pot equity and fold equity. So we can see in this question there's only one type of equity, which is our pot equity. So we can use the EV formula, it just ends up being quite long-winded. But seeing as there's only one type of equity mentioned in this question, we can just use our knowledge of pot odds to say, okay, 50 out of 200, that's 25% of the pot, therefore the break-even point must be at around 25% pot equity. But we've just demonstrated that using the EV calculation, using the algebra. So we keep talking about these slightly more complex scenarios where we have both pot equity and fold equity. So let's see an example. Here's a question. We're on the flop, 100 in the middle, so a lot of the parameters are going to be kept the same for the sake of simplicity. The difference here is we're the one betting now. The 100 in the middle, we're shoving all in for our last $50. And we expect to generate some fold equity. Sometimes we'll get called, but we also expect to generate some fold equity. So we expect to have 20% pot equity when called. However, we expect our opponent to fold 30% of the time against our shove. Question, is the shove plus EV? So we're definitely going to need to use the EV formula for this, but it's not going to be very straightforward defining our terms because, for example, when we deal with the term probability of winning, which term do we use? Do we use the term for our pot equity, 20%, or do we use the value for our fold equity, 30%? So I'm going to show you three different ways that you can approach this. Method number one is the two-step method. We calculate our expectation due to our pot equity first, then we calculate our expectation due to our fold equity using values we've derived from our pot equity calculation. Method number two we'll refer to as the three-bracket method along with a flowchart. The flowchart's probably optional, but we're going to use it to make this as simplistic as possible. Step number three, we're going to make use of my maths cheat sheet to see how we can accelerate all of this work. In fact, many of the short-handed calculations we're doing in this video can be accelerated using the maths cheat sheet. You just input the respective values into the Excel document and you get the answer put out. Step number one, the two-step method. So here's the question again on the screen. So we're shoving 50 into 100. And we mentioned we're going to split this into two steps. We're going to have a look at our expectation due to our pot equity first. So let's just imagine our opponent does call, the money goes in. What is our expectation after the money goes in? Expectation due to pot equity. So we're going to input our terms into the formula straight away. So just to recap on the defined terms. Probability of winning, 20% pot equity, 0.2. The amount we win, so that's everything in the middle apart from our $50. So that's $150 that we win. Subtract from that 0.8, our probability of losing by a process of deduction, multiplied by the amount we lose, which is $50. Multiply out the brackets, you can see our result is 10. In fact, the numbers are very similar to the one we've just looked at, where we get all in on the flop with 20% equity. The result's exactly the same, minus $10. So essentially, if our opponent does call, we know we're in for losing about $10. But that's only one part of the EV calculation here, because we also generate some fold equity as well. So the second step here is to calculate our expectation due to fold equity. We're going to put all of the numbers into a new formula, but when we get to the amount we lose, instead of using 50, we're going to use our calculated value, which is minus 10. So let's just go through these terms. 0.3, the probability of winning with respect to the amount of fold equity we have, multiplied by the amount we win. That's the 100 in the middle. We don't win our opponent's $50 if he folds. So 0.3 times by 100 minus 0.7, the probability that he calls, which we're going to define as losing, and the amount we lose, which is $10. We've established that in the previous part of the calculation. So we have a new EV calculation here. Multiply out the brackets, we get 30 minus 7 equals $23. So the EV of the entire scenario is we actually make $23. It's not good if our opponent calls. We effectively lose money every time he calls, but because he sometimes folds, the overall expectation is still positive. Now, one thing we have to address here is, what does that $23 actually mean? How should we interpret this number? Because right now, for most of us, it's just a number. It doesn't really have any meaning, $23. Does that mean we make $23 for the overall hand? Well, we could be forgiven for thinking that that's the case, that we walk away from the entire hand with an extra $23. That's not exactly what this means. This is our expectation relative to the current situation. We have to keep in mind that this is our expectation given that there is already 100 in the middle in the pot. Now, where did that $100 come from? Did someone just come down from space and put it there in the pot? No. We probably invested a decent chunk of that pot ourselves. In fact, in a heads-up scenario, we probably input about $50 of that, roughly half of what's already in the middle. So if we invest $50 into the hand on earlier streets, then on the current street, we walk away with an expectation of $23. What's our profit for the overall hand? We're actually down $27. So although it's better than folding, because if we actually check fold on this current street, if we just give up, our expectation is 0, which means that we're down $50 for the overall hand. Here, we can generate an expectation of 23, which is better than 0, but it still means we're going to be making a loss for the overall hand. Sometimes players get a bit confused about this, especially in relation to draws. Players think, for example, that if they have a break-even call with a draw, they should absolutely call because it's so much better than folding. They get to realize their equity. Well, that's absolutely not true. When you make a break-even call with a draw, you don't break even as such. You break even with respect to the current scenario, but when you look at the profits you walk away from the entire hand with, you're actually going to be down whatever you invested on the earlier streets. So understanding how to interpret what we get from these formulas is very important as well. It's one thing to understand the maths, but the maths is only relevant if we understand what the results the formulas are spitting out actually mean in terms of our actual profit and losses. Given that we already have a value here, $23, this is the expectation of this scenario. As we use the other two methods, hopefully we should also get the value 23. If we don't get the value 23, it means something has gone wrong with that calculation. So we're not doing this purely to get the result, we're doing this to learn the method. That's the whole point of what we're doing right now. So the next method is the 3-bracket method along with a flowchart. So same question here. Now before we start with the 3 brackets, I'll explain what that means very, very shortly. Let's just create a flowchart of all the possible outcomes that can occur in this hand. In fact, I've already done that for you. Let's have a look at this flowchart. So at the beginning of the flowchart, although it's not written, we shove all in for $50. Now at that point, one of two things can happen. Either villain can call, that happens 70% of the time, or villain can fold, which happens 30% of the time. If villain folds, it's the end of the game tree, and we win what's in the middle, which is $100. So overall, that happens 30% of the time. However, if villain calls, which happens 70% of the time, the tree doesn't end there, because there's two possible outcomes after villain calls. Either we could win by virtue of our pot equity, which happens 20% of the time, or we could lose, because villain's better equity holds up, which is going to happen 80% of the time. In terms of how often these two outcomes happen overall, we have to use a probability calculation. Probability of successive events, exactly what we talked about in the previous video. So to find the overall possibility that our opponent calls and we win, we multiply the respective probabilities of the successive events. So we multiply 0.7 times by 0.2 equals 0.14. So 14% of the overall time villain calls and we win. We'll now do the same thing for the outcome where villain calls and his equity share holds up and he wins the pot. So villain calls, that's 0.7 frequency, and villain wins 0.8 frequency. So we do 0.7 multiplied by 0.8. So 56% of the overall time villain calls and villain wins. So we have 3 outcomes there. We have an outcome where we win $150 14% of the time. We have an outcome where we lose $50 56% of the time. And we have an outcome where we win $100 30% of the time. Now the way the EV formula works is it can be expanded. Let's see how this happens. In fact, you can have as many brackets in the EV formula as you want to. Each bracket represents one possible outcome. So we can expand the EV formula like this. Probability of event A multiplied by the amount we win. Probability of event B multiplied by the amount we win. Probability of event C multiplied by the amount we win. We can just keep doing this. We can keep adding a bracket for every possible outcome. If, let's say, one of the events causes us to lose money, for the amount we'll just input a negative number, or alternatively it's possible to make the entire bracket subtracted and then use a positive number for the amount. Let's keep things nice and simple though. If the event represents winnings, we'll use a positive number for the amount. If it represents losses, we'll use a negative number for the amount. As we've seen, we've had 3 possible outcomes according to our flowchart, and we can input those into the EV formula. We have 3 possible outcomes, we therefore need 3 brackets. We're going to input the numbers we've just described. 14% of the time we win $150. 56% of the time we lose $50. Notice that it is represented as a negative number there in the second bracket. Then the third possible outcome, which happens 30% of the time, we win $100. Note that the percentages must add up to 100. If they don't, it means you've made some mistake in your probability calculation. So when we add 56 and 14, we get 70%. Then we add the remaining 30%, we get 100. So just double check that these numbers add up to 100. If they don't add up to 100, then your EV calculation is not going to work because you're missing out an event. Let's have a look at the way we can use the Maths cheat sheet to confirm this even further. This has also recently been rebranded as Weasel's Workbook. We're interested in this section of the EV Calculations tab. Expected value of a semi-bluff given known pot equity and fold equity. So let's fill in the values. Enter bet sizing. That's already as 50. Enter current pot size 100. Estimated fold equity. We said we're going to get folds 30% of the time. Estimated pot equity when called. It's going to be 20. There's 2 boxes here. EV is the second box. We can confirm that 23 is accurate according to the Excel document. Then we have this box, expectation due to pot equity. That was the first step of the EV calculation. So we can see that that's minus 10. We can confirm using the sheet that everything we've calculated so far is correct. So no need to do everything by hand in practice. You can just input the numbers into the Excel sheet. But it's also important that we have a working knowledge of how EV calculations are performed. That's why we've been doing it by hand so far. One final question, just as a test. We shove all in for $50 on the flop into a pot of 100. Everything's the same. We expect to get folds 30% of the time. How much equity do we need in order to break even? So you can see we're doing this question backwards. We're now thinking about our pot equity as the break-even point. And we can answer this just by doing the 2-step method, but backwards. So we start off with our expectation due to fold equity. We can actually just calculate the value on this sheet first so we know what we're working towards. So enter bet sizing here 50, enter current pot size before we bet. By the way, this section is required pot equity to semi-bluff given known fold equity. Well, we know our fold equity. Our estimated fold equity is 30. So we'll just change this box to 30 and the calculation should adjust. So it says here 3.57 pot equity required to break even. So we don't need a lot of pot equity, just 3.57%. And we can verify this is logical because if we think about betting 50 into 100 in general, that's a half pot bet. We know that if that succeeds more than 33% of the time, then we're generating automatic profit. So it's okay for our bluff to succeed less than that, given we have some equity, but we don't need a lot, given that we already get 30% fold. So we expect our break-even point due to pot equity to be quite low. So 3.57% seems a reasonable value. In order to do this by hand, we once again use the 2-step method, but we first calculate our expectation due to fold equity. So we do this 0.3 times 100, so probability of winning 30% times by the amount we win 100, minus, in the second bracket, probability of losing 0.7 times by the amount we lose. Now remember, that's going to be a substituted value. So that's x, that's what we want to find out, the amount we lose in this situation. So we're going to solve this for x. So we multiply out our brackets, we get 30 minus 0.7x equals 0. We can then get x onto one side of the equation. First of all, we can put that 0.7x over on the other side. So we get 30 equals positive 0.7x. Then we can do x equals 30 divided by 0.7, which equals 42.85714. So that's the amount we lose when called, but that doesn't tell us the pot equity we have. So now we go to the step of our calculation which we did first. We know that we're going to be losing money here, but our equity can't lose us more than $42.857114 in expectation. So we can run a new algebraic equation here where X is now the amount of pot equity we have. So we know the probability of winning, our pot equity is X, multiplied by 150 minus the probability of losing according to our pot equity, 1 minus X, multiplied by the amount we lose, our $50 investment, equals our negative expectation due to pot equity, which is minus 42.85714. Again, we're going to solve this equation for X. So first we multiply out the brackets. So we can add that 150 and 50x together. We can drag that minus 50 over to the right hand side of the equation, so it becomes positive 50. And notice it will now interact with that minus 42. So we end up doing minus 42 plus 50. We get the value 7.14285. We get 200x equals 7.14285. So we can now do x equals 7.14 divided by 200, and we get the value 0.0357. Of course, that's a decimal representation of our equity. If we multiply that by 100, we get 3.57, the exact same value that was given to us by the cheat sheet. So take some time to go over that slowly. We've gone through that quite quickly. A little bit complicated, might tie your head in knots, but if you can work through it and you can understand what's been done here, then it will improve your mathematical understanding of the game. So there is 3 things you should be able to do after watching this video, or at least have improved at. Number 1, understand the formula for EV and have it memorized. It's a super easy formula. There's only 4 terms. There's not really any decent reason why you can't memorize that. And if you can understand how you can make the formula longer as well by adding additional brackets, then that's great as well. Be able to calculate basic EVs, so this means actually use the formula that you've memorized, be able to understand how it applies in various poker situations. And also hopefully you've taken away a little bit about algebra. We've only done the absolute most basic possible version of algebra. Having said that, it could still be a little bit complex for some of you, but just persevere with it. It's not that difficult to do the algebra we've done in today's session. You just need to spend some time looking over those numbers until you understand what we were doing. Once you understand that, you'll be able to do it yourself. You'll be able to solve for break-even points using the EV formula. Okay, the next and final part of the Core Maths series will be an introduction to optimal play. In the postgraduate module of my course, we'll have a look at that in a lot more detail. But in this undergraduate course, it's just going to be an introduction to optimal play. So we're going to be doing a little bit more maths in the final part of the series. Then at that point, you basically know all of the basic maths you need to be playing poker in a competitive environment, and it's a good idea for you to proceed then to the next part of the course where we can look at specific strategies for beating online games. Alright, thanks very much for watching this video. Hopefully you enjoyed it. This was Weasel for PokerWeasel.com.